batteries. Any cell or battery, any term we can use. Sometimes it may be more than one cells connected in series, okay, that we use daily as a source of electricity. Basically it is a galvanic cell. Now galvanic cell means what? Which converts chemical energy from spontaneous redox reaction to electrical energy. So we know that there are two types of cell, galvanic cell or voltaic cell and electrolytic cell. Okay, so in the second type of cell, opposite process will occur, that is electric energy will be converted to chemical energy for non-spontaneous redox reactions. But in this case, in case of batteries, mostly it is galvanic cell where we will use some spontaneous redox reaction, and the chemical energy of this redox reaction that will be converted into electrical energy. Now there are some conditions. If these conditions are fulfilled, then only we can say that this is ideal battery. So what are the conditions? It should be reasonably light, because that will be easy to handle. It should be compact, and because for daily purpose this criteria must be present. Its voltage should not vary much during its life. Okay, so period of use, that means, so these points should be present when we are using any batteries. Okay, otherwise it will not be possible to use it on the daily basis, that is it is having some practical applications. So that is why all these points must be present. Now there are two types of batteries which we use mostly, primary batteries and secondary batteries, and under each category we will discuss one particular example which is most important. But first of all we have to know what is the basic difference between these two types of batteries. Primary battery versus secondary batteries. So when we are talking about primary cell, once the chemicals have been consumed, because we are using some spontaneous redox reactions, so after the reaction, when chemicals will be consumed, further reaction is not possible. Okay, so this is as if one time use. So after use, over a period of time, it will become dead and we cannot reuse again, just for one time. And it cannot be regenerated by reversing the current flow. Suppose once the reaction is complete, we have obtained electrical energy from chemical energy. Now if we want to regenerate by reversing the current flow, that is the reaction which is already from left hand side to right hand side, that is from starting material side to product side, already it is moved, starting material product. Okay, so this reaction is complete. But suppose we are trying to make starting material starting from product, but that is not possible here. And how we can do so? If we can apply current flow through the cell using external direct current source. That means now we are trying to do a non-spontaneous reaction by applying electrical energy. That is the opposite process, but that is not the case in case of primary cell. That we will see in the secondary battery, not in primary. So that is why it cannot be regenerated. It is just one time use. The most common example of this type is dry cell. So dry cell will be discussed in detail. But before that we will see what is secondary batteries. So secondary cell, when it is used, it can be recharged. Okay, so what is the meaning of recharged? It means that original reactants, that is original starting materials, we can again produce starting from the product side. And how we can do so? By passing direct current from external source, so that it can be used again. So if the secondary cell is very good, that means it can undergo a large number of discharging and charging. That means first it will be, that is when it will first operate, there will be discharging. Okay, so some energy it is already stored in the battery, so it will discharge, and once it is discharged, now we can do the non-spontaneous reverse reaction by applying direct current from external source. Okay, so this is discharging charging cycle. Then once it is charged, again we can convert that chemical energy to electrical energy. So this is a cyclic process, discharging, charging, discharging, charging. So larger is the number of these discharging and charging cycles, we can say that the cell is very efficient. The most important secondary cell is the lead storage battery, which is commonly used in automobiles and inverters. Okay, so one picture is here. Now under this secondary cell type, the example that will be discussed in detail, it is the lead storage battery, and also it is sometimes called as lead accumulator. Fine. So first we will see under primary battery what is dry cell. So as we are saying dry, and there is another name, try to remember it, because sometimes if this name is not mentioned, if it is mentioned Leclanche cell, then you have to understand these two are actually same. Now as we are saying the name dry cell, that means there is no liquid solution of the electrolyte that we normally see in case of other cell. Okay, so container of the dry cell, that is made of zinc. So if you look at the picture, zinc coating is present, and this is actually the anode. Okay, so the coating itself is anode. And what is cathode? That is the other electrode. The cathode is a carbon rod. So this is the carbon rod in the middle, in the center of the cell, surrounded by powdered MnO2 and carbon, that is manganese dioxide and carbon. So here we have carbon and manganese dioxide mixture. Next, the space between the electrodes, obviously there must be presence of some electrolyte, but as it is dry cell, it is not solution of the electrolyte, it is moist paste of ammonium chloride and ZnCl2, zinc chloride. Okay, that means here we have ions chloride minus, NH4 plus, ammonium ion, and Zn2 plus. Okay, so now we know what is the anode, which is zinc. Cathode is carbon rod, which is positive electrode or cathode, and the electrolyte paste, that is NH4Cl ZnCl2 mixture, and there is also carbon and manganese dioxide mixture, which is this one. Now we will see what are the reactions going on in the anode and cathode. So if we consider anode, this is oxidation reaction. So Zn is converted to Zn2 plus by sacrificing 2 electrons. Now these electrons will be utilized at the other electrode, that is in the cathode. Okay, so here these electrons are accepted by ammonium ion and it is reduced to ammonia. Fine. And here we can see that the hydrogen that is produced, that will be oxidized by manganese dioxide, because we have also taken manganese dioxide mixture. So ultimately 2 MnOH will be produced. Okay, you can also combine these two reactions together. So in some books you may also find these two reactions are written combinedly, but ultimately MnOH will be produced, and the zinc 2 plus that is formed at anode, that is making a complex with ammonia. Now ammonia is produced in cathode, so it will produce this type of complex, zinc amine coordination complex, and the cell has a potential of nearly 1.5 volt. Okay, so here you can see that electrons are coming from anode, because this is anode, this is the direction of electron, then it is light bulb, then electrons are going towards cathode. So this is the direction of electrons, so obviously the direction of current will be opposite. Fine. So this is all about dry cell, its working, its mechanism, and how it looks. Next is lead storage battery, or it is also known as lead accumulator. So this is example of secondary. So lead accumulator, it is a secondary cell because electric energy is not generated. See, already there is some stored energy that is converted to electric energy. It is not that in the dry cell that we have seen that in the medium, that is inside the cell, electric energy is produced, but in this case electric energy is not produced within the cell itself, but it is already stored in it from external source. Okay, that is the difference. And the net cell can be reversed if we can apply external opposite EMF which is greater than the cell EMF, because now we are trying to do the reverse reaction forcefully, because the reverse reaction is not spontaneous, but we are trying to do it forcefully, so that is why we have to apply opposing EMF and greater than the cell EMF, then only we can do it. And as the reaction is now reversed, so that is why it is also reversible. This cell can store electrical energy from external source, that is actually charging, and it can supply it by discharging. So when you are first using the battery, basically the first process is discharging, because already there is some stored energy. Now once it is complete, then we have to do the opposite non-spontaneous reaction by some external energy source, and that process is actually charging. Okay, so this is the picture of lead storage battery. So in this lead storage, this is a very simple diagram. Here we have anode and cathode. So here lead plate or grid packed with spongy lead, that means here we have only lead, oxidation state 0, and this, if this is PB lead, then that is the alternative plates, that is this one and this one, these two are PB plate packed with spongy lead. Similarly, if we consider cathode, then this is PB plate packed with PbO2. So that means now it is this one and this one. So it is alternatively arranged. So it consists of lead grid which is filled with spongy lead. This is anode. Okay, so this side is anode, and another one is lead packed with lead dioxide, that is PbO2. So in PbO2, oxidation state of Pb is +4, because we have 2 oxide and each oxygen atom has oxidation state -2. 2 oxygen atom means -4. So Pb must have positive charge +4. So this is the anode and cathode composition, and the electrolyte is here 38% solution of H2SO4. Okay, so this is a simplest diagram that is possible. You can also find some diagram of lead storage battery which is more complex than that, but this is the simplest diagram that is possible. So electrolyte is 38% H2SO4. Here this percentage is important. It is not just any concentration of H2SO4. This is 38% H2SO4. In the anode side we have Pb, that is 0 oxidation state, and in the cathode side we have lead which is packed with PbO2. So both Pb0 and Pb4 plus present at cathode. Okay. Now we have two separated, that is, the discussion will be done first on the basis of discharging, because when you are using the cell first time, it is actually the discharging, because already some stored energy is there. So discharging will be first, and then we will see what is charge, how we can do charging. So discharging, the cell now acting as voltaic cell, or you can say galvanic cell, because already there is some stored energy because of some spontaneous reaction which will be converted to electrical energy. So when the cell is discharging, it is operating as voltaic cell or galvanic cell, both are same. That means chemical energy is converted to electrical energy. Now the spongy Pb that is present at anode, that will be converted to Pb2 plus. Now look at the anode reaction. Pb, it is in 0 oxidation state, and now it is converted to Pb2 plus. And as there is sulfate ion present, because you are using electrolyte H2SO4, sulfate ion is present. In presence of sulfate ion, this Pb2 plus, that will be converted to PbSO4, and 2 electrons sacrificed by Pb. Now Pb2 plus ion, they can combine with sulfate and they will form insoluble PbSO4, and this begins to coat Pb electrode. These electrons that are removed from Pb0, now it will be utilized at cathode, which is PbO2, another electrode. So now PbO2 is basically +4. Now it is accepting this electron and in the medium there is already proton and sulfate ion because we are using H2SO4 electrolyte. So Pb4 plus, now it will be converted to Pb2 plus in the form of PbSO4 because sulfate ion is present. So Pb2 plus in presence of sulfate ion, it will produce lead sulfate. So see, in both anode and cathode PbSO4 is produced, but that doesn't mean that both the reactions are similar type. In case of anode, it is conversion from 0 state to +2 oxidation state, and in cathode it is +4 state is converted to +2 state. So basically this is reduction and this is oxidation. And if we add these two equations, the overall equation that we will get is Pb, just add these two, electron will be cancelled, Pb plus PbO2 plus 2 H2SO4, and in the product side 2 PbSO4 because from anode we are getting 1 PbSO4, from cathode we are getting another PbSO4. So 2 PbSO4 and water molecule. E cell is near about 2.041 volt. So it is greater than the dry cell, right? And if we want to represent the cell, it will be like this. That is Pb solid, which is electrode at the anode side. This is cathode side. Pb electrode, then PbSO4 because it is converted to PbSO4, and in the right hand side also PbO2 that is already present and it is converted to PbSO4, and in the middle we have the electrolyte that is 38% H2SO4. Okay. So after discharging, once all the starting materials are consumed, now how we can charge it again, that we will see here. So when it is charging process going on, it will act as electrolytic cell. That is another type of cell where where electrical energy is converted to chemical energy. That is opposite process. So this is another type of cell which is electrolytic cell, which is mostly used in electrolysis. Okay, all these discussions we have done already. So when external EMF, electromotive force greater than the EMF of the cell, if we can apply, now exact reverse reaction will take place. So in the previous slide we have already seen that in the overall reaction, lead sulfate is generated both from anode and cathode. Now what will happen? Now this lead sulfate will be converted to PbO2 and Pb. It will be converted to PbO2 in anode because it is oxidation. Pb2 plus is converted to 4 plus. This is oxidation. It will take place at anode, and in cathode side Pb0. That means from +2 you are reaching towards Pb0. So this is reduction which is occurring at cathode. So this is the opposite process. After many repeated charge discharge cycle, what happens? Some of the PbSO4 falls to the bottom of the container, and H2SO4 concentration also gradually becomes low. Okay, so the more we use the battery, ultimately one time we will reach that when the recharge will not be full. That is, it is not that all the products that is formed in the discharging process you can convert them 100% to the reactant side. It will not be possible the more old the battery is. So in the cathode, the reaction from +2 to +4, and in cathode, which is reduction, +2 to 0. And here the overall cell reaction, if you see, it is just the reverse reaction that we have seen in case of discharging process. Now PbSO4 H2O, it is in the left hand side, and PbO2 H2SO4 on the right hand side. So this is completely the reverse reaction. So this is the process of charging. Another type of cell, that is, it is not primary or secondary like that, it is completely different kind of cell, and it's from application point of view, this is very significant. Okay, fuel cell. But before fuel cell, we have to understand why this type of cell is introduced. There must be some disadvantage of some other cells, so that is why this cell is so important. So what are the disadvantages that we will see? So if we consider primary cell, main disadvantage is it can deliver current only for a short period of time, as long as the quantity of the reactants, that is the reducing agent, oxidizing agent, all these are present. But once they are consumed, you cannot use it any longer. Okay, so that is the disadvantage. And in case of secondary cell also, we have seen that the more old the battery becomes, gradually its efficiency is lesser and lesser. And in case of thermal plants, the chemical energy, that is the heat of combustion of fossil fuel. Fossil fuel means coal, gas, oil, all these are naturally available, that is why it is fossil fuel. So when these fossil fuels are burnt in air, that means in presence of oxygen, then combustion reaction takes place, which is highly exothermic in nature, that means high amount of energy is liberated. So this chemical energy is first used for converting water into high pressure steam, and this pressure which is generated from the steam, that is used to run a turbine so that electricity can be produced. So this is the very traditional method that is mostly followed in older days, but this is not very efficient method, and also it will cause pollution, because when you are burning these fossil fuels in presence of air, obviously there will be pollution because carbon dioxide will be generated. Okay, so these are the disadvantage of thermal plants where we use chemical energy from fossil fuel. So to get rid of all these disadvantages, there is introduction of fuel cell. So fuel cells are another means by which we can convert chemical energy to electrical energy. Now how we can do so? Here the source, that is the reactants that we will use, there is a continuous supply. So energy can be obtained indefinitely from a fuel cell as long as outside supply of fuel is maintained. So here we can supply the fuel continuously, and the most successful fuel cell uses the reaction of hydrogen with oxygen to form water. So here the final product is water. So it will not cause any pollution, unlike we have seen in case of thermal plants where carbon dioxide is generated, but here water is generated, which is pollution free. So this is the better side of this type of cell, and this cell can run continuously as long as we can supply the reactants. That means as long as we can supply hydrogen and oxygen. So hydrogen and oxygen here is these two elements are here reactants, that is starting material, and oxygen is directly not applied, it is applied in the form of air. That we will see when we will discuss the mechanism of fuel cell. And fuel cell produce electricity with an efficiency of about 70%, which is very good, and in case of thermal plants efficiency, it is almost half of it. Okay, so it is very less. So from considering all these points, you can understand how significant fuel cell is, because it is pollution free, and starting material, as long as we can supply it. Starting materials are also not very anything not difficult to obtain. So that is why from all these points of view, this is convenient compared to other cells. Now hydrogen oxygen fuel cell, this is the most important example under this type of cell, where starting materials will be used hydrogen gas and oxygen gas, but oxygen gas directly not used, it is used in the form of air. The cell consists of 3 compartments separated by porous electrode. Porous electrode means there will be some pores through which ions can be they can move. So look at this picture. So here from the left hand side we are supplying hydrogen, which is fuel, okay, and excess H2 that can also be recycled, because the excess H2 which is unreacted, that can be removed. So this excess hydrogen, it is removed from here. Now 3 compartments, this is one compartment, that is the anode compartment, then this middle compartment, and in the right hand side we have cathode. Now see here, hydrogen is denoted by these red atoms, then oxygen is by blue, proton which will be produced from hydrogen. When hydrogen will sacrifice electron, then this is this green dot, and this yellow part, that is the electron which is removed from hydrogen. So hydrogen is giving electron and itself is converted to proton, that is H plus. Here the electrodes are made of porous carbon and the electrolyte is resin containing concentrated aqueous NaOH solution. That means in the electrolyte you have HO minus ion. Fine. So the H2 gas that we are supplying from the left hand side, it is introduced in one of the compartment, that is the anode compartment, and oxygen gas in the form of air that will be supplied from in the cathode. Okay, that is fed into another compartment. Now at the cathode, hydrogen molecule, they will be converted to H plus and electrons, that you can see in this picture, that the green dots are actually moving towards cathode, because in the cathode we know reduction takes place. So obviously some electron will be required. So the electrons are moving from anode side to cathode side, and from oxygen ultimately it will react with hydrogen, that is a net reaction if we consider, and reaction between H2 and O2, ultimately there will be formation of vapor. But we will see what are the separate reaction going on at cathode at anode. But if you consider the net reaction, it is actually the reaction between H2 and O2, and final product is what? So here the excess oxygen which will be unreacted, that can also be recycled. Okay, so air and water vapor that are liberated in the right hand side, that you can see. The H plus ions migrate through the electrolyte to the cathode. Okay, so H plus ions are these green atoms, where they unite with oxygen, and also it requires electron because H plus is electron deficient, so that it can produce H2O, and heat is also generated. Fine. Now we will see what are the actual that is individual separate reactions going on at cathode and anode. So reaction at anode, as we have supplied H2 in anode, and in the electrolyte there is already presence of hydroxyl ion. So these two together will make water and electron is produced. Now this electron will be utilized at cathode, and in the cathode side we have supplied oxygen gas. Water is already there, so this reaction will take place and ultimately HO minus will be generated. So if we add these two equations, basically you have to multiply this equation with 2, then you can add, because we have to cancel the electrons ultimately. So here we have only 2 electrons, so just multiply with 2, then add these two equations. Suppose this is equation 1, this is equation 2. If you add these two equations, you will get this equation, because here HO minus, this side it is 2 into 2, that means 4 HO minus, and here we have in the right hand side 4 HO minus, these two will be cancelled. So ultimately there is production of 2 H2O, that is here we will have 4 H2O, this is 2 H2O, so 4 H2O minus 2 H2O, ultimately 2 H2O. So this is the net cell reaction. Now we will see what will be the value of the E cell, that is in the ultimately what will be the value after combining individual reduction potential value of anode and cathode. But for that we require electrochemical series. So here we have some partial electrochemical series. So I have taken only that part where you will find these two reactions and their potential, cell potential. So look at this reaction. O2 plus 2H2O plus 4E equal to 4HO. So this is this one. And what is the corresponding reduction potential? It is 0.4. So this is the reaction which is going on at cathode, and the anode, which is actually oxidation. But as we know that in electrochemical series we always consider by IUPAC convention, it is always the reduction reaction. So for this one it is this one. So the corresponding reduction potential minus 0.83. So see, this system it is written in reverse order, H2O 2E, because always we write in the reduction reaction form, not in oxidation. So this is the value, and that we know that the reduction potential value which is present in cathode system, that should be always higher than this, because otherwise the net E cell it will not be positive. Okay, So if we want to know what is E cell, we have to add, we have to subtract E naught of anode from E naught of cathode. So for cathode it is 0.40, for anode it is minus 0.83. These two will be cancelled, that is minus minus, so ultimately it will be 1.23 volt. So for fuel cell, this is the cell potential. Finally we get that is combination of anode and cathode. Fine. Now we will see some application. Fuel cells can be used in a wide range of applications. So power for applications across multiple sectors like transportation, automobiles, industrial, commercial, residential building. So household purpose will also be served. Long-term energy storage for the grid in reversible system. Fuel cells having several benefits over conventional combustion-based technologies. Combustion-based technologies means we are talking about power plant. Okay, so it has several benefits over this conventional traditional method. So that is why it is so important, and research is going on this fuel cell. So maybe in future it will be some more benefit we can get from these fuel cells. Now this chapter is complete. We will discuss some problem. Corrosion is also there, but corrosion I have already discussed when we have application of electrochemical series. Corrosion is already discussed. So here the problem is potassium chlorate. Potassium chlorate means KClO3. Can be prepared by electrolysis of KCl in basic solution, and this is the reaction by which we can get ClO3 minus. ClO3 minus is nothing but KClO3. Mostly you will see in cell reactions only the anion is written, because K plus is not important here. The oxidation state of chlorine is important here, so that is why we are focusing on this part. And electrolysis of KCl, that means the anion is Cl minus, so that is mentioned here. And as it is basic solution, so HO minus is already written. So the equation, balanced equation is already given. Here chlorine from -1 oxidation state, it is converted to, what is the oxidation state here? It is +5, because overall charge is -1. Fine. 3 oxygen atom, per oxygen atom it is -2 charge. That means -2 into 3, it is -6. So 1 negative charge extra, +5 -6, 1 negative charge extra. So that is why overall charge is minus. So for this reaction, suppose we are using some current, but the current is 60% efficient. That means the total current that you are supplying, only 60% is actually utilized. That means its efficiency is not 100%, it is 60%. The time we have to find out, which is rounded to nearest hour. Remember, this must be expressed in hour, which is required to produce 10 gram of KClO3 using a current of 2 ampere. So here current amount is given, we have to find out time, and some values are also given. For example, this Faraday, Coulomb per mole, molar mass of KClO3. This is if it is given, it is better, because after, otherwise you have to find it yourself. Okay. Now for this reaction, as we can see, for formation of 1 mole of ClO3 minus, we need 6 electrons, and 1 electron is actually having charge 1 Faraday. So 6 Faraday charge must be required. 6 mole electron, sorry, it is mole, required for generation of 1 mole KClO3 according to the reaction given. So in terms of Faraday, if we see, it will be 6 Faraday charge required for 1 mole KClO3. But we have to find out the time for 10 gram of KClO3. But 10 gram of KClO3 we have to convert it to moles, then only we can understand it is actually how many moles. Number of moles of KClO3 equal to given mass. Given mass is 10 gram divided by its molar mass, which is 122. Okay, just you can keep it like this. And here, as okay, let me calculate, it is 0.082. Now as efficiency is 60%, that means what? We have to supply current more than 6 Faraday, because whatever we will supply, that will not be utilized 100%. Okay, so as 60% is the efficiency, that means when you require 60 Faraday of charge, what you supply? You supply 100 Faraday. So when you need 6 Faraday, you have to provide 10 Faraday according to this relation, because it is 60% efficient, so we have to supply some more amount, which is clear. Now when we know that it is 10 Faraday, we can convert it to corresponding charge. But before that, we will find out that for 0.082 mole, what will be the required Faraday. So for 1 mole KClO3 required Faraday 10F. 0.082 10 into 0.2 Faraday, and this is simple calculation, 0.82 Faraday. So now we know what is the amount of charge required. Now the equation Q equal to IT. I means current in ampere, T is time in second, and Q is charge in coulomb. But Faraday, if we want to convert it to coulomb, what you have to do? 0.82. It should be multiplied by this value, because it is a very large unit of charge, and we have, before applying this equation, we have to convert it to coulomb. So in the left hand side we have written this, and current, it is mentioned in question, 2 ampere. T unknown, basically T we have to find out, right? So from this calculation, T will be 39,560 second. We know that 1 hour is basically 3600 second. That means it is 60 into 60. So if we convert this second to hour, what we will do? We will divide it by 3600. So it will be about 10.99 hour. So it is mentioned rounded to the nearest hour. That means ultimately the value will be 11. So it's 11 hour. Okay. So this is an integer type of problem where the final answer is 11. Next problem. 108 gram silver. Molar mass is given, which is also 108 gram per mole. And this amount of silver deposited at cathode. That means what? From AgNO3. That means at cathode this reaction is going on. That is why metallic silver is deposited by a certain quantity of electricity. the volume of oxygen gas produced in liter at this temperature and pressure which is mentioned from water by the same quantity of electricity is. That means we have to find the volume of oxygen which will produce from water. So this is a completely different system. But what is the common point between these two cells? The common point is the current amount that you are using in the first cell for reduction of Ag plus to silver. You are using the same current. So first of all, you have to find out the current. Okay. So once you can find out the current, then you have to write the balanced equation of how oxygen is produced from water. And once you know the balanced equation, you know for 1 mole of oxygen production what is the number of moles of electron required. And once you know the number of moles of electron required, you can easily find out what is the charge required in Faraday. And electricity you have already known. So we can calculate how many moles of electrons are required to produce O2 from H2O. Now once you know the number of moles of oxygen, you can use the equation PV equal to nRT, which we use for gaseous molecules, and from that relation you can find out the volume, because here temperature is given, pressure is also given. So you can use PV equal to nRT, that equation. First of all, we will find out number of moles of silver deposited. So given mass is 108. Molar mass is also 108. So it will be 1 mole. Ag plus, accepting 1 mole electron, and it is producing 1 mole Ag. So we can say that 1 Faraday charge will be required to deposit 1 mole of Ag, because 1 Faraday is nothing but the charge of 1 mole electron. Now this is the first equation. Now the next, that is the second system, that is how H2O can be converted to O2, that we will see here. Okay, so here H2O, it is basically oxidized to oxygen, because see, in H2O, what is the oxidation state of oxygen? It is -2, and in the right hand side it is 0, that means it is oxidation. H2O contains H plus, and H plus is still in H plus form, that means there is no change in case of H plus, but oxygen from -2, it is now oxidized to O2 0, that is the elemental state, and 2 electron removed. Now for half mole of oxygen, the requirement of electron is 2e, right? So when we want to get 1 mole of oxygen, you have to provide double electron. So for half oxygen it is 2 electrons, so if it is 1 mole oxygen, it must be 4 electrons. Okay, so we have to balance the equation first, or alternatively we can say that 2F charge can deposit half mole of oxygen, because 2 electron charge, corresponding charge is 2 Faraday. So we can say 2 Faraday charge, when we apply, we will get half mole of oxygen. So when we are applying 1 Faraday charge, because 1 Faraday is the charge that we are getting in the first process, because we have to use the same charge, we cannot change the amount of electricity. So that is why we have written that 2F charge can deposit half mole of oxygen, but we have only electricity amount 1F, not more than that. So it can produce 1,4 moles of oxygen. Now use the equation PV equal to nRT. N you know, this is N. P is 1 bar, already given in the question. V is unknown, that we have to find out. R is, we know what is the value of R in liter bar unit, and that is liter atmosphere, it is the same, and T is 273 Kelvin. So put all these values, that is the value of N, value of R, value of T, value of P. So finally what you are getting, this is the volume of oxygen. 5.675. Here it is not mentioned nearest integer, but if it is mentioned, then it will be 6. 5.6, it will be 6. How long a current of 3 ampere, current amount given, which is I. How long means time we have to find. How long has a current of 3 ampere to be applied through a solution of silver nitrate so that we can get a coating of metal surface, that is coating of silver. Silver is plus oxidation state, but when it will be metallic silver, it will be 0, that means it is reduction. To coat a metal surface of 80 centimeter square, that is the area, and thickness is 0.005 millimeter. This is in centimeter, this is in millimeter. Be careful about the units. So here what will be the amount of silver, metallic silver, that is given, but not directly in the form of weight. Normally what we see that to deposit this amount of metal, what should be the required electricity, but here amount is not given. Here it is given that what is the area and the thickness. So if you know the area and thickness, you can easily find out volume, and if you know the volume and density, you can easily find out mass, because density is given in the question. Okay, so first we will find out the mass, because we know the volume from these two and density already given, so we can easily calculate mass. So mass of silver to be deposited, that is volume into density, because density is mass by volume. So mass will be D into V. This is D, this is V, this is M. Now volume is basically area into thickness. Okay, so in place of V, now we will write area, where area is 80 centimeter square given in the question. Thickness is 0.005 millimeter, very small value, but millimeter you have to convert it to centimeter, so 0.005 is now 0.0005. So put all these values. Density is already in centimeter cube unit, so ultimately the value that you will get, the mass of silver is 0.42. So this 0.42 gram, that is not directly given in the question, it is given in some other form. After this, now once we know what is the weight, we can find out the number of moles. Number of moles of silver. Silver is 108, given mass 0.42 divided by 108. So this is the number of moles. If you can calculate it, it is fine, but you can also put this value in the next step, so that you can do only one, that is you will do the calculation only once, but it is up to you whether you want to do it stepwise or finally you will do the whole calculation together. So if this is the number of moles, then charge required, that is also this amount of Faraday, because number of moles equal to Faraday. Okay, so if this is Faraday, convert it to Coulomb, we will multiply with 9650 divided by 108. Now it is in Coulomb, right? So if we know the charge, now from this equation, Q equal to IT, T we have to find out, right? Q value known, I is known, T is not known. T is Q by I. What is Q? This is Q. 0.42. Current is 3 ampere. If we do this, you will get so whenever you are using this equation, the value of time that you will get, it will always be in second. because the equation, it is correct only when T is in second. So that is why the result that we will get by using this equation, that will always be in second. Okay. Next problem. A 100 watt 100 volt. What is unit of power? 100 volt voltage. Incandescent lamp is connected in series with an electrolytic cell which contains cadmium sulfate solution, CdSO4 solution. Okay, CdSO4 means what is the oxidation state of cadmium here? Cd2 plus, because sulfate is having charge -2, so it must be +2. What mass of cadmium, that is cadmium 0, will be deposited by the current flowing for 10 hours. So time is given, but it is given in hours. Atomic weight of Cd is given 112.4. Now we have to know what is the relationship of watt, ampere and volt. So watt, ampere and volt, it is related by this equation. So basically here volt and watt is given, but we require ampere. So ampere we can get by using this equation. So it is 100 divided by 110. So this is ampere. So quantity of charge, that is ampere into second. That means this is actually the equation Q equal to I into T. Q is quantity of charge, I ampere, T second. So in place of ampere we have written 100 by 110, then multiplied by 10 hour, but it must be converted to second, so that is why it is multiplied by 60 into 60, which is nothing but 3600. So when we multiply all these values together, we will get the corresponding quantity of charge. Now the reaction here is Cd2 plus, which is present in CdSO4. So from 2 plus it is now reduced to Cd in cathode. So this that is when 2 moles of electron produced, when 2 moles electrons are utilized, we are getting 1 mole of Cd. That means 1 mole Cd means, look at the atomic weight value, it is equal to 112.4 gram. So this must be the weight. So to produce this amount of cadmium, we require 2 moles of electron. That means we require 2 Faraday of charge. And here we know what is the charge in Coulomb, but we will convert it to Faraday. And how we can do so? Charge in terms of Faraday. Here charge is present in terms of Coulomb unit, but if we divide it 10 into 16 to 60, that means 10 into 3600. If we divide it by 96500, because 1 Faraday is equal to 96500 Coulomb, so that is why this is the Coulomb charge. We are dividing it by 96500. So now we can get the value in Faraday, which is 0.339 Faraday. Okay. Now 2 Faraday can produce 112.4 gram Cd. 0.339 Faraday can produce 12.4 divided by 2 multiplied by 339. So this amount of Cd will be produced, and this value is 19.0 19.04 gram. So in the question it is the question is what mass of cadmium will be deposited, that is metallic cadmium in zero oxidation state. So the answer is 19.04 gram cadmium can be produced.